Hello, my name is Camila Friedman-Gerlicz, and I'm going to be presenting WeaveSlicer, expanding the range of printable geometries in clay. This work was completed at the Hand and Machine Lab in the Computer Science Department at the University of New Mexico. WeaveSlicer is a slicing software that expands the range of printable geometries in clay. It allows us to print forms with more extreme overhang angles, like this bowl form you can see. On the left, WeaveSlicer is printing it and the form is complete and upright, or on the right, a traditional slicer is causing the form to collapse. When 3D printing in clay, clay must be wet and soft, and it remains that way for a long time until it dries due to evaporation. Clay is also really heavy, and therefore many forms with extreme overhang angles are prone to collapse when printed out of clay. Because of clay's properties, there are limits on what forms can be 3D printed out of clay using traditional and commercially available software. Forms like those on the left that are more vertical can be printed more easily because each subsequent layer is fully supported by the layers below. Vertical forms like the vase made by Amy Traylor on the right can be successfully printed in clay. Forms like those in the middle of the diagram are harder to print because layers are not supported by those below it, so they collapse. This limits the type of geometries that can be 3D printed out of clay. WeaveSlicer was motivated from my time as an artist in residence in the Hand and Machine Lab from the summer of 2022. I am a ceramic artist who makes sculptures based on algebraic surfaces that are defined by math equations. These forms have complex geometries and often have rounded tops and bottoms. I came into the residency eager to try to 3D print these forms in parts and then assemble them later. So the first summer I used Cura to slice these parts up and print them. I printed them with lots of infill because they were rounded and had lots of overhang angles, so they needed support from the inside. The toolpaths and infills were all generated by Cura, which wasn't designed for clay 3D printing, and so sometimes some of the toolpaths didn't quite make sense with the material of clay. Since clay is malleable and can be hand worked, I made it work with this slicing technique. So again, after things were printed, I would carve out all the infill that was left over and then assemble the parts as well as smooth out all the texture from the 3D printer. I was interested in the forms being kind of mimicking their mathematical smoothness. One thing I found, though, in the summer of 2022 is that while the printer would print the infill, each layer would then, the outside layers would dry, and the adhesion to the next layer was not as good. And this manifested in cracks after the firing process that didn't show up until the firing process. I returned to the Hand and Machine Lab as a researcher in the summer of 2023, and I was motivated to find a better way to slice and print these forms. This process began by observing how traditional clay 3D printing works. So in traditional clay 3D printing, layers of equal width, and that width is determined by the nozzle size of the printer, are extruded around a form. So this can be seen in the vertical cross-section shown here. Each of those brown ovals is the same width. What we noticed, though, is that this actually created thinning of the walls in areas with more dramatic overhang at like the top and bottom of that figure. I have over 2 decades of experience in making things out of clay, and so when thinking about 3D printing, I took motivation from other ways of making things out of clay, like wheel throwing, coil building, slab building, and slip casting. And in all of these methods, it is ideal to have walls of uniform thickness, as can be seen in this second image. To achieve this, we would have to have variable layer thickness throughout the form. So we set out to build a software that can print walls of uniform thickness. We achieved this by using a sinusoidal toolpath, as can be seen here. The thickness of each layer can then be determined by the amplitude of the sine wave instead of the nozzle width. This allows for layer widths to adapt as the form changes. So the workflow of our slicer works like many other slicers. It is run in the Rhino and Grasshopper environment, and first the user inputs a 3D model into the slicer. Then the user sets various print parameters that are common to most slicing software, like what printer we're using, the nozzle size, extrude rate, speed, layer height. Then the user sets WeaveSlicer parameters that are unique to this slicing software, like wall thickness and period of the sinusoidal curve. WeaveSlicer then outputs a G-code file that the 3D printer can read. WeaveSlicer computes that file in the sinusoidal toolpath by first finding the amplitude or layer thickness at every point. It does this by finding the vertical intersection of the form at that point, as can be seen in the middle zoomed in picture. It uses n, which is the wall thickness, and that is a parameter that is set by the user, so it is constant. It then finds the angle between the tangent line to the vertical intersection and the horizontal line parallel to the print bed, theta. A is the amplitude of the sine wave at that point that it is trying to find, and it just uses this simple trig equation to calculate A. After it has done that, then it takes each point on the curve and moves it normal to the horizontal contour by its amplitude. This individual amplitude calculation allows for the layer thickness to vary within a form and even within each layer. So the width of the layer will increase when the form has a more dramatic overhang, as can be seen in the middle of this video, this form in this video, and decrease when the wall is closer to vertical, like on the right and left sides. So while it looks like the form might be thicker in the middle, if you took a cross-section of that form, it actually has uniform thickness. WeaveSlicer also has some toolpath adjustments, and some of those can be controlled by the user, like this one, where the user can control whether the toolpath is going to be centered on the contour. So that means some of the toolpath is inside the form and some is out, or sit inside the contour curves, which just means that your print will be more accurate to your 3D model. It also adjusts for moments like this, where if there's a sharp angled turn, the sinusoidal wave from one side might go outside of the form on the other side. So WeaveSlicer adjusts for that and pulls that toolpath inside the form. It also adjusts for moments where the amplitude of the toolpath might be longer than half the distance to the center of the curve, or from the distance from the outside of the curve to the center. So it also adjusts for that and makes sure that there's no over extrusion of the material by going beyond where it needs to. Once we finished the software, we wanted to test our software, and so we used 2 different 3D printers and 2 different clay bodies to do that. So the 3D printers we used were the 3D Potter 10 Pro and the Ezhou 0. The 3D Potter has a plunger that pushes clay out of the nozzle directly. The consistency of clay is pretty hard and can be similar to what would just come out of a normal clay bag. The Ezhou has a plunger that pushes clay through a smaller tube, and then a second motor that controls an auger, which is a screw that pushes clay out of the nozzle. The consistency of the clay used for this machine needed to be much softer, closer to a thick frosting consistency. Both of these printers are commercially readily available. The first form we tested were simple bowls with various overhang angles. So we started at 45 degrees and went to 15 degrees. For our tests, we used 2 different clay bodies. We used a mid-range white stoneware for the Ezhou, as can be seen on the left, and a low-fire red earthenware for the 3D Potter on the right. Since the nozzle for the 3D Potter was twice as large as the nozzle for the Ezhou, the tests on the 3D Potter were twice as large. The WeaveSlicer was able to print bowls with overhang angles less than 45 degrees, whereas the traditional slicer failed for all of the forms that were less than 45 degrees. We fired all of these tests and they survived the firing. Here are our 3 tests, each on the 35-degree overhang, and these tests have been fired. We also wanted to test half spheres to see to test what happens when the overhang goes in instead of out. These half spheres have overhang angles ranging from 0 at the bottom to 90 degrees at the top. We used WeaveSlicer to slice them and print them and compared them to half spheres sliced with a traditional slicer like Cura. WeaveSlicer was able to print a stable and complete dome without any slumping or collapse and no infill or supports. Whereas the traditional slicer started slumping and eventually collapsed towards the top. These tests were also fired without any cracks or problems. We took these tests and cut them in half to look at the cross-section of the half spheres, and we can see that the one with WeaveSlicer on the left has a completely uniform wall thickness, and this was an exciting kind of verification of our diagrams from the beginning. The one on the right, which is printed with a traditional slicer, you can see the wall starts thinning out towards the top before it eventually collapses. After our tests, we decided to go back to my artistic work to do applications. I remade the horned torus, the envelope surface, and the Klebisch diagonal cubic, which are defined by the equations below. So here is the workflow from the summer of 2022 compared to the summer of 2023. So in the summer of 2023, I was able to print the same form with far fewer pieces. I only printed it in 2 parts. And those parts could be printed completely using WeaveSlicer with no collapsing and 0 infill. So it took a lot less time. And as I assembled it, there still was post-processing. I still smoothed out the forms and assembled parts, but WeaveSlicer allowed for a streamlining of this post-processing and resulted in a form that did not have any cracks. I was able to fire and glaze this piece without any problems. I used the same process to print the envelope surface, where again, I've printed it in parts and smoothed them out, and then fired them and glazed it, and fired it again. And here's the Klebisch diagonal surface, which again used the same process. This one was an open surface, and so the open raw edges can kind of show the uniform thickness that WeaveSlicer was able to achieve. We also had 2 resident artists in our lab this past summer, and they both experimented on some of their forms using WeaveSlicer. So one of our resident artists was Jeff Suina. His Instagram is right there. And he was making geometric forms and exploring how to 3D print them for the summer. This form began to collapse when he printed it with a toolpath generated from a traditional slicer, as on the left. So we decided to print it with WeaveSlicer, and you can see the form remained very rigid with no collapse. Our other resident artist was Monica Silva Lovato. She used WeaveSlicer to slice and print this form, and then used the texture it left as a decorative element by choosing only to smooth part of the pot. So the pot on the left is before it was fired, and the pot on the right was after it's fired, using a pit firing technique. In conclusion, we found that WeaveSlicer is an incredibly versatile and useful tool. We were able to print many different types of ceramic objects, from vessels to sculpture, and WeaveSlicer allowed us to print forms that would have been impossible to print out of clay in any other way. We used our deep material knowledge of clay to design a slicer that greatly expands the range of printable geometries in clay. Thank you so much.